proteins. It's given a random noise input, and the AI figures out a brand new protein that does what you asked it to do. This work has huge implications. I mean, imagine you got bitten by a venomous snake. If you're lucky, you'll have access to antivenom, prepared by milking venom from the exact kind of snake, which is then injected into live animals, and the antibodies from that animal are extracted and refined and then given to you as an antivenom. The trouble is, often people have allergic reactions to these antibodies from other organisms, but your odds of survival can be a lot better with the latest synthetic proteins designed in Baker's lab. They've created human-compatible antibodies that can neutralize lethal snake venom. This antivenom could be manufactured in large quantities and easily transported to the places where it's needed. With these tiny molecular machines, the possibilities are endless. What are the applications you're most excited about?
So I think vaccines are going to be really powerful. We have a number of proteins that are in human clinical trials for cancer, and we're working on autoimmune disease now. We're really excited about problems like capturing greenhouse gases. So we're designing enzymes that can fix methane, break down plastic.
What makes this approach so effective is how fast they can create and iterate the proteins.
It's really quite miraculous for anyone who's a conventional old school biochemist or protein scientist. We can now have designs on the computer, get the amino acid sequence of the designed proteins, and then in just a couple days, we can get the protein out. Yeah, we've given a name to this, which is cowboy biochemistry, because you just got to kind of go for it as fast as you can, and it turns out to work pretty well.
What AI has done for proteins is just a hint of what it can do in other fields and on larger scales. In materials science, for example, DeepMind's GNOME program has found 2.2 million new crystals, including over 400,000 stable materials that could power future technologies, from superconductors to batteries. AI is creating transformative leaps in science by helping to solve some of the fundamental problems that have blocked human progress.
If you think of the whole tree of knowledge, there are certain problems where, if they're root no problems, if you unlock them, if you discover a solution to them, it would unlock a whole new branch or avenue of discovery.
And with this, AI is pushing forward the boundaries of human knowledge at a rate never seen before.
Speed-ups of 2x are nice. They're great. We love them. Speed-ups of 100,000 times change what you do. You do fundamentally different stuff. And you start to rebuild your science around the things that got easy.
And that's what I'm excited about. These discoveries represent real step function changes in science. Even if AI doesn't advance beyond where it is today, we will be reaping the benefits of these breakthroughs for decades. And assuming AI does continue to develop, well, it will open up opportunities that were previously thought impossible, whether that's curing all diseases, creating novel materials, or restoring the environment to a pristine state. This sounds like an amazing future, as long as the AI doesn't take over and destroy us all first. This is a video about one of the most important. A single sentence in one of the oldest math books held the key to understanding our universe. Euclid's Elements has been published in more editions than any other book except the Bible. It was the go-to math text for over 2,000 years. But for all that time, mathematicians were skeptical of a single line, which seemed like a mistake. Ultimately, some of the greatest math minds realized that Euclid wasn't wrong after all. But there was more to the story. Slight tweaks to this line opened up strange new universes out of nothing. Surprisingly, 80 years later, we found out those strange new universes are core to understanding our own universe. Around 300 BC, the Greek mathematician Euclid takes on a massive project to summarize all mathematics known at the time. to essentially create the one book that contains everything that everyone knows about mathematics. But that's no easy task. See, before Euclid, there was a bit of a problem with math.
People would prove things, but they would just be going around in circles. Why does a triangle have 180 degrees? Because if you take two parallel lines, yeah, but why do parallel lines exist? Oh, that's because you can make a square. Why does a square exist? You have this infinite recursion of what the fundamental reason why something is true is.
It's kind of like in the dictionary. Every word is defined in terms of other words. So how do you get to ground truth? Euclid used a solution that was pioneered by the Greeks. Let's just accept a few of the most simple, basic things as being true. These are our postulates. Then, based upon these postulates, we can prove theorems, one at a time, building up our math using logic. So that as long as those first statements are true, then everything else that follows from them must definitely be true. He had perfected the gold standard for rigorous mathematical proof that all modern math relies on. Euclid used this method when he published his 13-book series called The Elements, in which he proved 465 theorems covering almost all of mathematics known at the time, including geometry and number theory. And all these theorems depended on were some definitions, a few common notions, and 5 postulates.
We go right to book 1, and book 1 starts with definitions. You gotta start somewhere. And the definition is: a point is that which has no part. A line is a breadthless length, and the ends of lines are points. By line, he really means a curve, and then it has some ends. A straight line is a line that lies evenly within the points on itself, and then so on and so forth. He's got 23 definitions, then he's got the 5 postulates.
The first 4 are simple. 1, if you have 2 points, you can draw a straight line between them. 2, if you have a straight line, you can extend it indefinitely. 3, given a center and a radius, you can draw a circle. And the 4th is that all right angles are equal to each other.
But postulate 5 gets the big guns.
Which is that if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which are the angles less than the 2 right angles.
What the hell is he talking about? That's a postulate? Like, all of these are, half of a sentence, and they're all blatantly obvious. And then comes 5, out of left field, and it's like an entire paragraph. What is he doing?
This made mathematicians suspicious. It seemed like Euclid made a mistake. Greek philosopher Proclus thought postulate 5 ought even to be struck out of the postulates altogether, for it is a theorem. But if it's a theorem, we should be able to prove it from the first 4 postulates, so that's what many people tried. Some, including Ptolemy and Proclus, believed they had succeeded, but they hadn't. In fact, all they'd managed to do was just restate postulate 5 in different words. Here's one formulation. If you have a line and a point that is not on that line, then there is a single, unique line which will be parallel to the first line. For this reason, the 5th postulate is often called the parallel postulate. When the method of direct proof failed, other mathematicians, including Al-Haytham and Omar Khayyam, tried a different approach: proof by contradiction. The idea is simple. You keep the first 4 postulates the same, but assume that the 5th postulate is false. Then you use those new postulates to prove theorems. And if that leads to a contradiction, for example, true equals false, well, then it means your new 5th postulate must be wrong. And therefore, the only remaining option would be that Euclid's version of the 5th postulate is correct, and you would have proven the 5th postulate. So what would it look like if the 5th postulate were false? Well, according to Euclid, through a point not on a line, there could only be one line that is parallel to the first. One alternative is that there are no parallel lines that you could draw through that point.
Well, people tried that, and they realized that then lines had to be finite in length. And they're like, well, that can't be.
So this option was ruled out. It contradicted the 2nd postulate, which states that lines can be extended indefinitely. The other alternative is that you can draw more than one parallel line through a point not on the first line.
So that's what they would do. They would assume that postulate 5 fails. And they're like, this has got to be wrong. Where's the they couldn't find the contradiction.
So proof by contradiction also failed. In total, mathematicians spent more than 2,000 years trying to prove the fifth postulate, but everyone who tried failed. Then, around 1820, Janos Bolyai, a 17-year-old student, started spending his days and nights working on the mystery. His father became worried, and he wrote to his son, "You must not attempt this approach to parallels. I know this way to the very end. I have traversed this bottomless night, which extinguished all light and joy in my life. I entreat you, leave the science of parallels alone. Learn from my example." But the young Bolyai didn't listen to his father. He could not leave the science of parallels alone. After years of work, he realized that maybe the fifth postulate can't be proven from the other four. It could be completely independent. See, according to Euclid, you could have only one parallel line through a point, but Bolyai imagined a world where there could be more than one parallel line through that point. But how? Well, who said you needed to have a flat surface? On a surface that is curved like this, you can draw more than one line that is parallel to the original line. But wait a second, those lines don't look straight. Well, what makes straight lines special is that they're the shortest paths between 2 points. On this surface, those shortest paths just look bent because the surface is curved. Here's a more familiar example. Airplanes always try to fly the shortest path between 2 cities. They're basically flying in a straight line, but that line doesn't look straight on a map because the surface is curved. These shortest paths on curved surfaces are called geodesics. So all these lines are straight, they just don't look it because the world Bolyai had imagined turned out to be curved. We now know this as hyperbolic geometry. You know, when I used to think of the hyperbolic plane, I would just imagine it as one giant saddle. But that's not really what it is. The hyperbolic plane is much more like this piece of crocheting. So it starts out pretty flat and even in the middle, but as you move outwards, more and more fabric is created, and that would push parallel lines apart. And the further and further out you go, the amount of fabric grows exponentially, and that ends up causing this crumpling effect. So if you really want to think about the hyperbolic plane, I think you've got to think about saddles on saddles on saddles, like it's an infinite crumpling mess. But that little piece of crochet isn't the full hyperbolic plane. To show that, we need to make a map, one that fits the entire plane into a disk. To show how this works, we're going to fill the entire plane with these triangles. Starting in the middle, just as with the crochet, things look pretty normal. But as you go farther out from the center, you get all this extra space, so you can fit more and more triangles. So they appear smaller, but they are actually the same size. Now, since the hyperbolic plane is infinite, you can keep adding triangles forever, and they all need to fit on the disk. So as you get closer to the edge, the triangles will appear smaller and smaller and smaller. Infinitely smaller, never ending, and you can never quite reach the edge. This is known as the Poincaré disk model. Here, straight lines are arcs of circles that intersect the disk at 90 degrees. And just like on our original shape, a straight line down the middle appears straight, while straight lines next to it appear to curve away. What's remarkable is that Bolyai didn't have a model of hyperbolic geometry yet. He was just drawing Euclidean triangles with the assumption that Euclid's fifth postulate didn't hold. And while Bolyai found that the behavior in hyperbolic geometry is very different than Euclid's, mathematically it seemed just as consistent. In 1823, the 20-year-old Janos wrote to his dad, "I have discovered such wonderful things that I was amazed. Out of nothing, I have created a strange new universe." But Bolyai had been doing more than just tackling ancient math mysteries. In his 20s, he joined the army, where he continued developing two of his other passions, playing the violin and dueling. He had mastered both, but with a sword in particular, he was unmatched. Perhaps because of his many talents, Bolyai grew arrogant and found it difficult to accept authority from his superiors. That made him hard to get along with. This reached a peak when, during one of his deployments,
When I started my research in semiconductors, I thought that because chips were everywhere, chips were easy to make, and because nuclear bombs are only controlled by a handful of governments, they were hard to make. But what I realized is actually the exact opposite. If you take nuclear weapons, that technology has barely improved since the 1960s. It's so easy to make nuclear bombs, even the North Koreans can do it. But chips are everywhere because they're cheap and they're tiny. And making things very inexpensive and very small is extraordinarily difficult. Today, there are just 3 companies capable of producing cutting-edge processor chips, the types of chips that go in phones or computers or are used for AI. For many of those devices, they rely on chips that in some cases can only be made by one company in a single factory in Taiwan. The key risk that hangs over not just the chip industry, but really our entire economy is that something goes wrong between China and Taiwan and the Taiwan Straits, such that we lose access to chips made in Taiwan. My name is Chris Miller. I'm a professor at the Fletcher School and author of Chip War, the fight for the world's most critical technology. Well, I first got interested in chips when I realized you really couldn't understand how the world works without them. When we think about technology, we think about social media, we think about search engines, we think about apps on our phones, but undergirding all of this are chips. A chip is a piece of silicon, often the size of your fingernail, and in it is carved thousands or millions, in some cases billions of tiny devices called transistors, which flip circuits on or off, on and off. And when they're on, they produce a 1. When they're off, they produce a 0, and all of the ones and zeros undergirding computing, undergirding data storage, all of your Instagram likes, all of your text messages. These are all just long strings of ones and zeros, which are created on the chip by these circuits flipping on and off. Before transistors, computers used vacuum tubes, which are sort of light bulb-like devices that would turn on and off to produce the ones and zeros. They were cutting edge for their time, but they had huge inefficiencies. They wasted a lot of heat, for example. They worked pretty slowly. And they also, because they created light, attracted moths. And so computers had to be regularly debugged in the early days of computing, which meant removing moths from the lights that they were attracted to. In the middle of the 20th century, William Shockley, John Bardeen, and Walter Brattain invented the first transistor while they were working at Bell Labs. It was part of AT&T at the time.
Invented at the laboratories, the transistor brought Bell scientists one of the 2 Nobel Prizes they have won for discoveries in physics.
They were initially planning to use these transistors as part of the telephone network.
Though it was primarily developed for the betterment of telephone communications, the versatile transistor now appears in a staggering variety of devices and equipment.
Individual transistors were connected via wires in a way that was okay if you had a handful of transistors, but if you had 1,000 connected together, you had a jungle of wires you had to manage. The first chips were invented by engineers working at Texas Instruments and a company called Fairchild Semiconductor in Silicon Valley. The first engineers realized that you could take multiple transistors and make them on a single piece of semiconductor material. And so that was the first chip, a piece of material with multiple transistors carved into it.
This single silicon crystal will be trimmed, then sliced and diced. The objective, semiconductors. Patterns are made by a photographic process and then micro-machined by chemical etching to produce nearly 1,700 transistors on each slice.
And so the jungle of connections was replaced by a single block of material, which was much more reliable and also much more easy to shrink in its size. At first, they were building chips primarily for the US government, for the space program, for example, and for weapon systems, but they realized early on you could take the exact same chips that the government wanted to guide spacecraft and use them for commercial applications like computers or pocket calculators. And that set the industry off into its first phase of growth in the 1960s and 70s.
All the calculator know-how you'll probably ever need.
Over time, a new set of companies emerged. Intel, for example, was founded in 1969, and it quickly focused on making chips for personal computers, which at the time was a very small market, but they correctly bet that soon everyone would have a personal computer. And Intel, even today, is the world's largest producer of chips that go inside PCs. Gordon Moore was one of the 2 co-founders of Intel. He's most famous today probably for coining the term Moore's Law. Moore's law is not a law of nature, it's not a law of physics, it's really a law of economics. Moore's law predicts that the number of transistors per chip, and as a result, the computing power per chip will double every couple of years. And that's been empirically true since the 1960s. If you're able to find a way to shrink your transistors smaller, you will be able to find a larger market as well. And that has incentivized huge investments in shrinking, in improving manufacturing processes, and making chemicals more purified, which means that the capabilities of chips have gotten vastly better and continue to get much, much better at a faster rate than anything else. So I like to think, for example, of airplanes to illustrate the difference. If airplanes doubled in speed every 2 years from the 1960s up to the present, we'd be flying faster, literally, than the speed of light. But chips have done that. Chips have increased in that capability because the scale of the transistors has shrunk. Chips today are measured in nanometers. And so that makes them only slightly larger than atoms, far smaller than bacteria, smaller than a mitochondria, half the size for the most cutting-edge transistors of a coronavirus. There's basically nothing we manufacture at such tiny scale. When you go inside one of these massive facilities called fabs, what you find is that there are huge machines and not much else, because humans are way too imprecise for manufacturing at nanometer scale. The machines that make chips can cost $350 million a piece. And they cost so much because they require some of the most precise components ever used, like a mirror that's the flattest mirror humans have ever made, a laser that's the most powerful laser ever deployed in a commercial device, and a ball of tin that falls through a vacuum and then is struck twice by that laser, explodes into a plasma measuring 40 times the temperature of the surface of the sun. And this plasma emits light at just the right wavelength, 13.5 nanometers, to be bounced off the mirrors in exactly the right geometry and land on your chip to carve the transistors into the silicon. It's the most complex and expensive machine that humans have ever made, and it's required to make all of the most advanced chips. And that has enabled the explosion of computing power, both in terms of the computing capabilities in high-powered data centers or in your phone, but also the application of computing to all sorts of devices. Today, there's computing everywhere. It's in your dishwasher, it's in your refrigerator, it's in your coffee maker, it's in your car. And it's possible to put computing everywhere because today it's so cheap. We can produce it almost for free. The chip industry was a global industry from really the earliest days. Because chip making requires ultra-purified materials and hugely complex equipment, everyone requires a set of partnerships to give them the materials and the intellectual property and the software and the tools that they need to produce advanced chips. So in the US right now, most of the key chip firms only design chips. Most of the manufacturing of chips happens in East Asia, in Taiwan, for example, or in Korea. Many of the chemicals that go into chip making come from Japan. And the machines that are used to make chips come from either Silicon Valley, where some of them are still made, or the Netherlands or Japan. So the industry has globalized, but it's also specialized in the process. And so there's not a single region today that can make cutting-edge chips on its own. If you take, for example, the primary processor inside of your smartphone, it was probably made in Taiwan, but it was made in Taiwan using chip-making tools from the Netherlands and from the United States and from Japan. It was produced using chemicals from Japan, and then often assembled and packaged in Malaysia before ending up inside of your smartphone. And that's typical. During the pandemic, the supply and demand dynamics around the chip industry were out of whack. A lot of people ordered new computers, for example, to work from home, and so PC production shot up in ways that weren't expected. Or people bought fewer cars in the early days of the pandemic, and so car production declined, and companies couldn't predict what type of chip they would need. The effect of that was to create shortages of certain types of chips. Car companies in particular found they couldn't get the types of chips that they rely on. The thing about cars is if you're missing just one chip, your car often doesn't work. And during the pandemic, car companies found themselves often in that situation. Just a single chip, often even the cheapest chips, were causing them to have to leave cars in the factory parking lot as they waited for the right chip to arrive. That created hundreds of billions of dollars of losses for manufacturers like automakers. And that matters because the Shortages we saw in 2021 and 2022 are tiny in comparison to the shortages we would see if something happened to a large-scale chip maker like those in Taiwan. The biggest chip maker in the world is the Taiwan Semiconductor Manufacturing Company. Now, when it comes to advanced processor chips, like the chips in your phone or the chips in your computer, TSMC makes around 90% of them. In 1987, there was a American engineer named Morris Chang. The Taiwanese approached him and said, "Would you like to build a chip factory in Taiwan?" And he said, "Yes." At the time, most chips were manufactured and designed by the same companies. But he established TSMC in Taiwan with the aim never of designing chips, only of manufacturing. That's exactly what TSMC has done, and it's enabled TSMC to win among its customers some of the largest companies in the world. Apple, Nvidia, Qualcomm, AMD, they all rely on TSMC